Hello, this is required derivation number 5. It actually is a summary of all things simple harmonic motion and simple harmonic oscillators. Let's consider a mass hooked to a spring oscillating on a frictionless surface. The first picture shows a spring which is hooked to a wall and also our mass, and the spring is in a relaxed position, so it's neither compressed nor stretched. Stretching the spring out by pulling the mass and then letting go produces this force diagram, and that is what generates the mathematics for simple harmonic oscillators. So we have F net equals ma, and the only horizontal force is the spring force. When we make a positive displacement x, our acceleration is in the opposite direction, and so writing a as the second time derivative of the position function, and I like to use the dot notation, so a double dot or x double dot, along with some algebra yields what I call the signature simple harmonic oscillator equation. And once you get this format, then you can, of course, use this general solution. And below here, I show how this general solution will work for this differential equation as long as omega squared is equal to k over m here. And so we now have a solution for the position as a function of time, the velocity as a function of time, which is the first time derivative of the position function, and the acceleration versus time, which is the second time derivative of the position function. On this second slide, I rewrite the signature simple harmonic oscillator equation with the solution that works for x of t, with the condition that the constant that multiplies our function x is equal to omega squared, and then recognizing that omega is always equal to 2 pi over the period, I can generate an expression for the period of a mass oscillating on a horizontal surface. Here's an example to consider when working with simple harmonic oscillators. Initial conditions allow you to figure out various things. For example, suppose that the position is at the equilibrium position and the mass is moving with a velocity of negative 3 meters per second at time equal to 0. If you're given the mass and the spring constant, then we can find the position as a function of time, the amplitude, and the phase shift as shown below. And so this is a nice example to look over when you are looking at how to apply initial conditions. The first required derivation was the mass oscillating on a horizontal surface attached to a spring. This is the second required derivation, and that is finding the physics behind the physical pendulum, which is an arbitrarily extended mass object oscillating about a pivot P with its center of mass located some abstract or arbitrary place on the object surface. So in this physical pendulum situation, when it's disturbed by a small angle theta from hanging straight below the pivot, then there will be a restoring torque that causes it to go back to its equilibrium position. And this restoring torque is equal to I times alpha. The torque is about the pivot, and so I must be measured about the pivot. And the only force that causes a torque is this gravitational force. So I have drawn over here the diagram showing the relationship between the gravitational force mg down and the lever arm of the torque r, its direction. And so we can get an expression for the torque, which is r cross f, or r being the distance between the pivot and the center of mass, which I've labeled b here in the picture, times the weight, which goes right here, times sine of theta, which is part of your cross product. So if we replace our torque expression here with bmg sine theta, then we get I times alpha, which is also I times theta double dot, and that's equal to the net torque minus BmG sine theta. Here's where we incorporate our small angle approximation that says for small angles, sine of theta can be replaced by theta, and now we have our relationship simplified in this line here, and of course, a couple of algebraic maneuvers later, we have our signature simple harmonic oscillator equation. You note the functions or variables second time derivative plus a constant times the variable is equal to 0. So we already know the solution to this. I'll just write it down here, where of course omega squared is equal to this constant that multiplies this variable. And so we have a way to find the period for any arbitrarily shaped physical pendulum. If we can find the moment of inertia about the pivot, frequently that involves the parallel axis theorem, as well as the distance from the pivot to the center of mass. Here are three different scenarios where knowing how to derive the physical pendulum will allow you to figure out the period of physical pendula that are oscillating about a pivot. Here's a rod, and you can see that the rod is oscillating about the pivot P, and we have just generated for any physical pendulum this relationship right here. So we can start there, and using our ability to find the moment of inertia about the pivot, here you see the parallel axis theorem invoked. We get the period of the rod. If you take a hoop and pin it and allow it to oscillate about a point P, again, we implement the parallel axis theorem and our derived equation for any physical pendulum's period to generate the period of this particular system. And finally, we have a disk, which is a hoop filled in with mass, and so the center of mass is 1/2 mr squared, and so that allows us to find the moment of inertia about the pivot, which we then stick into our physical pendulum period relationship, and we're able to get the period of this physical situation. If we want to discuss the energy of our simple harmonic oscillators, usually there is a kinetic energy and there is an associated potential energy. And for the mass on the spring, for instance, the kinetic energy at any time can be evaluated by just taking 1/2 times mass times velocity squared. Substituting in our relationship for the velocity as a function of time, we get a general expression for the kinetic energy. Likewise, for the elastic energy, 1/2 kx squared, if we substitute in for x, the x of t function, and square it, then we get an expression for the elastic potential energy. Of course, the total energy at any time is just the sum of those two, and if we actually add this up to this, then what we find is that the total energy is always equal to the elastic energy when the mass is fully compressed or stretched. Our final slide shows the graph of the elastic potential energy of a mass on an oscillating spring. You can see U is graphed against S or X, and if the graph is graphing 1/2 kx squared, you can see the parabolic nature of this graph. We always have a total energy at the extremes at either A or negative A, and so this line here represents the total energy. And since the graph itself shows you the value of the elastic potential energy, then the kinetic energy is going to be the difference between the total energy and the value of the elastic energy. And that's nice to do graphical evaluations.